Okay, so let's start. Any questions from last class? Okay, so we were discussing about a broad overview of an RF chain, and we started off from the acoustic part, that is, we want to transmit our, let's say, voice signal. Then we said that we are going to convert it into currents and voltages, and then we also said that just transmitting currents and voltages of the audio signal that is thus generated through a wireless channel is not feasible, because the antenna that is required will be, the size of the antenna is of the order of kilometers, a few maybe tens of kilometers. So that is not something that is a very practical solution. So the suggestion was, if the frequency relates to the antenna, and higher the frequency, smaller the size of the antenna, then it's probably feasible to increase the frequency and thereby get the size under control. So then we saw that in order to do that, we need some nonlinear operation or some maybe time variant operation. The time variance part we haven't talked about, but at least we know that if you use nonlinearity, then some sort of frequency translation can be done. And that is something that we can use to move the desired frequency of operation to a higher frequency, right? So that is where we ended. And we will again keep going in the same vein. Even today's lecture will be on a broad overview of what an RF chain looks like. And hopefully sometime middle of next lecture, we will complete the overview and then move into more details of circuit design. Okay, so we were at this junction that we have a signal which has been generated from some desired waveform, which was acoustic in the example that we were taking. So this waveform, if I call it V in, had a frequency component of, had a spectra rather, V in had a spectra limited to, let's say, 10 kilohertz. 10 kilohertz is also being generous when we are talking about audio signal. But let's say this is, if you do not want to cut off anything, any frequency component while speaking, 10 kilohertz does a decent job. But 10 kilohertz led to very high size of the antenna. So we wanted to ensure that this 10 kilohertz stuff gets translated to some frequency, let me call it FC, somewhere around FC, right? So the solution was, the suggested solution was, yeah, it's coming. If we have this to be V in T, and let's say I call this VCT, where V in T is whatever the baseband signal is, or the input signal is, and VCT is a frequency of, is a signal of a different frequency. Let's call this VC cosine 2 pi FCT. And we pass it through one known block that we are familiar with, let's say common source amplifier. And I have not shown the biasing on the input side. So don't think that it is going to work as is. And we limit our discussion to, if I add a biasing also, maybe to complete the discussion, we better add a biasing. So I call this VB. And we observe this current IDS, or rather the total current IDS. Then what we observed was, our IDS was, if the transistor is in saturation and blah, 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 and we ensured that that's the case, then IDS was half mu n C ox W over L, V in plus VC plus VB minus some threshold voltage whole squared. And I'm neglecting the channel length modulation here. And if I expand this out, what would I get? I'll get mu n C ox W over L. And then I get the DC term, that is VB minus threshold voltage whole squared, plus I get another term which contributes to the linear linear part of the incremental current, that is 2 times VB minus VTH plus V in plus VC, right? And then we get another term plus V in plus VC whole squared, right? So if I remove the bracket, so this first term clubbed with this term gives the DC biasing current. So this is IDS. Let me call it IDSQ. This term, when it comes out, gives you, sorry, this is a multiplication, right? Why did I write this? Okay, pay attention. Call me out, basically. So this term gives you mu n C ox W over L VB minus VTH times V in plus VC. So this is essentially GM times the incremental input, plus you get V in plus VC whole square. Okay, times whatever. Times half mu n C ox W by L V in plus VC whole square. Question? Okay. So now the reason I wrote it out is because in your experience of doing analog circuit courses before, when a transistor is biased in saturation and all those good things are met, among these three terms, which in your opinion is the strongest? All are current, three current terms. Which term is the strongest? Biasing, right? Typically, that's what it is. And I shouldn't make a generalized comment, but let's say that is the strongest. It will not be far off, right? So the first term is greater than either of the two terms. What about the middle term? The middle term is higher than the last term, or middle term is lower than the last term? Middle is higher. Why? Yeah, it's not particularly amplitude of the signal, but per se, I mean, when you are designing amplifiers, you would like to ensure that the distortion part is low, right? And one might say I can bias the transistor in a very distorted regime, but from whatever we have learned in analog circuits till now, we expect that the distortion part, which is the last part, will be negligible with respect to the linear part, right? So, which means this is greater than this, and this is finally, this term is obviously the minimum. Now, in order to translate in frequency, which term do you want it to be the strongest? The last one, right? Because the last one gives you the frequency translation. So effectively, you would want the last term to be strongest. To ensure high efficiency. I will define efficiency shortly. Or rather, I should say mixing is desired. Okay. So if that's the case, then when I say efficiency, I essentially mean that, by the way, even if before I give the definition of efficiency, what do you understand by efficiency?
Input power that we draw from the supply, they wanted to convert it into a useful signal power.
Okay.
So from 0 hertz, we want to convert it to a useful signal power of some frequency.
Okay.
So, and we wanted all of the power that is drawn from the supply to be converted, to be sent to the load.
Sure.
To useful signal.
Sure.
All of them means, so we expect it to be 100%.
Right. Yeah. So you are right, but I would even generalize it. I would say that in any system, you have certain, the total power anyway is conserved, right? That goes into a system. Some amount of the power goes in generating the desired signal, and rest of the power goes in generating undesired stuff, right? It can be DC, it can be other frequency components, right? So essentially, the power which contributes to the desired divided by the total power is your efficiency, right? So obviously, if the desired power seems to be the minimum among all the three terms that is contributing to the power consumption, then obviously this is not a very highly efficient circuit, right? So that is one of the reasons, and that is the primary reason these type of circuits are not used for mixing in general, right? I should not again make a blanket statement. Sometimes they are also used in some niche applications, but this is not a general practice to use these type of circuits for frequency translation. Again, I'm not sure whether I mentioned this terminology in the previous lecture. This operation of multiplying two signals is called mixing, right? So if I say that I have one signal V in T, and I have another signal VCT, essentially what we are trying to do is we are trying to get a mathematical multiplication going, and this output, which is V in T times VCT, will have this combination will have a frequency which is different from either of V in T or VCT, assuming both V in T and VCT are not DC to start off, right? So otherwise both have DC, right? So this operation is called mixing operation. This multiplication, mathematical multiplication in terms of when we translate to RF language is called mixing. So obviously the mixing operation that we saw 5 minutes back is not a very efficient one. That operation was leveraging nonlinearity, right? So the next thing that I would like to focus on is, this is something I talked about in the previous lecture, that is, you cannot have frequency translation in an LTI circuit, LTI system, that is linear time invariant system. So we chose to break nonlinearity. And then we saw that some sort of frequency translation is happening, but not very efficient. So we will try to break the time invariance, right? And then see what happens. So when I say time invariance, without getting too deep into mathematics, what I essentially mean is, let's say I have a system. I'll go with an example. Let's say I have a system, or a network N, and I have a input and let's say this, without lack of generality, without losing any generality, let's say this is some sinusoid or some sinusoid V in T for the time being. We'll generalize it later on. So if I apply V in T now, I am going to get some current I in T. And how do I know what this current is? This current is essentially, if I know the input admittance, let's say the input admittance is G, right? So I in t is essentially G times V in t, right? This I can always write, okay? So, if a system is time invariant, it essentially means that I do the experiment now, I will get this relation, and let's say the G is, I don't know, maybe 1 millisiemens or 2 millisiemens or whatever, 2 microsiemens. You put a number, right? So I put in V in t. I am going to get 1 millisiemens times V in t now. I do the same experiment 1 day from now. I'm going to get the same result. I do the experiment 1 microsecond from now. I'm going to get the same result, right? So this is essentially what time invariance means, right? I shift the input or shift the observation time, and if I shift the input with respect to where any time axis that you decide that you design, and the output will also shift in time accordingly. Okay, but then what does time variance means? Time variance essentially means that I do the experiment now, I get some output, and I do the experiment 1 microsecond from now, I'm not going to get the same output. So that's all time variance means. Okay, so let's keep only that part in mind. Now, if I look closely between these two cases, in the case on the top, we are essentially desiring a mixing operation, and in the case in the bottom, we are not getting any mixing operation. But if we want a mixing operation, what do you think needs to happen? If I only concentrate on the term on the bottom and try to relate it to the term on the top.
G should be time
G should be time variant, right? So this is multiplication. All I need to know is make G time variant. Okay. So for mixing, G should be time variant, i.e., we need G of t, right? So ideally, if we need G of t, now what type of time variance are you looking for here? When I say time variance, I can say that G of t is, let's say, 1 millisiemens now. After some time, it goes to 2 millisiemens and stays like that. Is that kind of time variance you're looking for? Or is there any specific time variance you're looking for? Some sort of periodic. Why some sort of periodic? Exactly, right? So essentially, it need not necessarily be only periodic signals helping frequency translation, but periodic signal gives you tones. When I say tones, I mean from periodic signal, you get specific sinusoids, right? So ideally, we would want G of t to be some G, which is constant, times some cosine 2 pi fct. Right? So let's say I call this G naught times cosine fct. This is ideally we want. If that is the case, then naturally you see that I in t is a multiplication of V in t times some cosine fct. That gives you frequency translation. But as it turns out, this is not a very straightforward job. Generating a G of t which varies exactly like a sinusoid is not a very straightforward job, right? So what people then decided is if this is not something that we can generate easily, what is the next best thing that we can generate? So as it turns out, in a chip or in any electronic design, the most easily generatable, the periodic signal that you can most conveniently generate is a square wave, right? All of you have done multiple courses, digital IC and so on. So you see that if you need a square wave, all you need is basically a bunch of inverters. You put them and give any periodic signal at the input, the output will be a square wave, right? One might say that the duty cycle might not be 50%, but it's okay. We'll still get a square wave, which is periodic. Okay, all you need is some periodic signal at the input. Fine. So if that is something that we can look forward to, then all we need is so if g of t can be a square wave, then what is the easiest way to generate is a g of t that is square wave? What I'm essentially saying is that if this is a square wave, g of t can be maybe some g1 here and g2 here, and it periodically does this, right? So what is the easiest way to generate this? So basically what I'm looking for is what should be in the box when I apply, let's say, a DC voltage. You can have any voltage, doesn't matter. I mean, any test voltage. I will not limit myself to DC. This current will be, so I in T will be if I, let's say V test is, you pick your type of signal. I pick some sinusoid maybe. Right. So this is, let's say, V test. Your I in T will be what? Let's say G1 equal, let's put some numbers. Let's say G1 equal to 1 millisiemens, and let's say G2 is equal to 10 millisiemens, right? So what would I in look like? So I in probably will follow as is here. And then what will happen here? It will suddenly increase by 10x, right? So it will suddenly increase by 10x and go here. And then again, this will change its amplification factor in terms of current, and then suddenly decrease and maybe do like this, and again suddenly increase by 10x, and obviously this is not to scale. Something like this is going to happen, right? Okay, fine. So which essentially means that here I am getting in these domains, I am getting I in T times 1 millisiemens. Here I am getting I in T times 10 millisiemens, and so on, right? And by the way, when I write it in terms of I in T times 1 millisiemens, I'm assuming that this is limited to within that chunk of time, not any generalized time, okay? So what should this box look like if I need a waveform like that? Yeah, fine. So we can have switches and resistors, but we use switches and resistors, you can design anything. So any particular combination of switches and resistors? Anyone else? No, I basically want a G of T, which looks like a square wave.
So maybe we can do a comparison with the high frequency sawtooth. So we can
Much simpler, much simpler.
charge and then
Okay, much simpler. Pardon? What are you going to compare with what?
Comparing this V test with the sawtooth high frequency square triangular wave, maybe that can
Comparing this you generate, you need another waveform of, and then do what with that?
So, then, so can you do comparative maybe
The output of the comparator will flip.
between 0 to 8?
So that I am already, okay, so for that you require two waveforms. One sawtooth waveform. Sawtooth is also not very simple to generate, right? The simplest thing to generate in an IC is a square wave. So let's say you have a square wave, right? You have a square wave available to you. Yes.
You can use one transistor, connect this to the drain. And
Okay.
to the gate of the transistor, you can use the higher part of the square wave would allow a current to pass through, which should be equal to.
Okay, so can you repeat again? So I have a transistor. What do you want to give where?
At the gate, we give the square waves that you can generate.
Okay.
And at the drain, we connect the meters
Okay.
and source is grounded.
Okay. Yeah. So this, let's say, goes from 0 to VDD.
Not 0 to VDD, but VDD to something else.
Okay.
Give 10 millimeters a month.
Okay. So this goes from, tell me something. So the lower part, do you want it to be? I'm asking for this voltage. VDD by 2 to VDD. Okay. And why do you say VDD by 2? What was the thought process behind that?
It will still be above threshold to allow point.
It could be still be above threshold to allow some current, right? Okay, good. So that is some, I mean, do you agree that this kind of work, right? So if you have some, if the transistor is, let's say, always on, you are basically changing the amount of the amount of on resistance, right? So when you have the input to be, this gate voltage to be VDD by 2, let's taking his example. By the way, what is your name? Pardon?
Vasudev.
Vasudev. Okay. So if I take the example that Vasudev suggested, so when you have the input to be VDD by 2, maybe you have some R on. When it goes to VDD, it have a different R on, and hopefully a smaller value of R on. And this R on keeps on, the on resistance keeps on switching from between two values, which means I have two different values of G, right? So this actually is what we call it a switch, right? But the operation right now that we are seeing here is not that of an ideal switch. An ideal switch is the one where it turns off completely and then turns on, right? Turns off and turns on, right? So an extension of this is that of a switch. So we can basically say that, let's say I have a switch. I'm not drawing any transistors till now. So for this illustration, let's say we have a switch, and let's say I have some resistor here connected, right? So this is V test, and let's say the switch, I say that ST is a square wave. I'm extending whatever he said with slightly different values. Let's say this is 0 and this is VDD. Okay. So all this is doing is when ST is 0, right? The assumption is that the switch threshold is somewhere between 0 to VDD. So let's say this is switch threshold. Okay. So if ST is below the switch threshold, your switch is off, which means if switch is off, what is G? If this is, again, looking in is G of T. Yeah, switch is off, your impedance is infinite, which means the admittance is 0. Your G of T is 0. And your switch is on, right? Switch is on. If it's an ideal switch, no on resistance. What is G of T? 1 over R, right? So let's call it G naught. And this guy goes. So, okay, fine. So if I have G of T, I know I in of t. And this I in of t flows into R. So this if I take this voltage V naught of t is I in of t times G of t. Fine. Okay. So then what? So G of t is not a sinusoid. G of t is a square wave, right? So the next thing will be to say that I will provide, since we know that a periodic signal, right? A periodic, not an aperiodic signal, a periodic signal can has multiple frequency components, multiple discrete frequency components, not spread across all frequencies, but tones. So which essentially means that I can break G of t into multiple tones, basically Fourier series, right? So I can even simplify this further slightly. So I can say that this is G naught times I in of t times ST. The reason I am writing in the forms of ST is because ST, I can say that ST is a digital logic which goes from, maybe I should not write ST, I should write something else because ST is defined as 0 to VDD. So let's say I say SD of t. Right, where SD is a waveform which goes from 0 to 1. This is just for simplifying the algebra, right? I do not want to carry forward the G naught every time. Okay, fine. So how do I decompose this waveform into multiple sinusoids? We know that this is periodic, so we will know that SD of t will be summation of some an e to the power j 2 pi some fc times nt, where fc is 1 over tc, where again tc is the period of st, right? When I say period, I essentially mean the fundamental period, right? It is periodic with what is the minimum amount of time for which it is periodic with. If something is periodic with tc, it is also periodic with 2tc. It is also periodic with 3tc, but we are looking for the smallest one. Okay. Okay, fine. So this is nothing new. This is, I assume all of you know from your basic communication courses. So what is an? How do I get an? So an goes from minus infinity to infinity here. So an is 1 over 1 period. It can go from 0 to tc ISGT times e power minus j 2 pi fcnt and integrated over time. Right? So if I do that, what do I get? Do you know the expression offhand? We can do it 1 over tc 0 to tc. So it's 0 to start off, and it goes from between tc by 2 to tc. So basically, I should say it goes from tc by 2 to tc, which is 1 times e to the power minus j 2 pi fc and t dt. This tc and this fc combine to cancel each other. So I get numerator, I get right. There shouldn't be any. Why? Oh, yeah, right. Yeah, thank you. Yeah. So if I expand this out, I get. So this term cancel each other. E to the power minus j 2 pi n, where n is an integer, is always 1. So 1 minus e power j. Again, fc and tc by 2 gives 2 pi. 2 pi over 2 is pi. Sorry, it gives 1, and this becomes minus j pi n, right? Okay. So if I take e to the power minus j pi n by 2 out, so this kind of very nicely fits into this format. And this term is 2j times sine pi n by 2. So what all things cancel? This will. So this essentially becomes minus e to the power minus j pi n over 2. J also cancels. Times sine pi n over 2 by pi n. Right, so this is your an. This essentially means that, again, let me write out st in this format, sd of t rather, summation of an e to the power j 2 pi fc and t over all n. This essentially means that I have broken this down into tones, and strength of each tone, this strength of each tone is essentially equal to an. Again, just to ensure that we all are in the same page, what is the Fourier transform of e power j 2 pi fct, let's say? Yeah, so this is delta f minus fc, and which essentially means that if I plot the spectrum of SF, right, ST rather, I call this mod of SF. I'm not interested in this part. So this part mod gives 1, so they don't come into picture. So if I plot this, I should get some A naught. Then I should get A1. So by the way, what will be the strength of A naught? Yeah, right. Why half? Because you essentially can break this down into this by 2 times 1 over 2, right? So when n tends to 0, that is the sinc function that goes to 1, that 1 over 2 remains. So this is half. Then what is A1? This is at 0. So A1 will be located at FC. What will be the strength of A1? So sine n pi by 2, n is 1. So sine pi by 2, which is 1, divided by pi n. N is 1. So 1 over pi. So 1 over pi. Similarly, for negative frequency also, you are going to get the same strength if I take the magnitude. So this is FC. This will be 1 over pi. Right. So what about n equal to 2? That is at 2 FC. Yeah. So I put n equal to 2 in that top expression. So I get sine pi, which means 0. Nothing is there. What about 3 FC? 1 over 3 pi. And similarly, I'm going to get here 3 pi and so on, right? You will get, for every odd FC, you are going to get 1 over the location of the harmonic times pi, right? Okay, so why are we doing this? The reason we are doing this is ultimately it's a multiplier. So I'm multiplying a signal whose spectrum is this with another signal, which is audio frequency of audio range, whose spectrum is something, the positive spectrum is like this. So, I mean, since it's a real signal, the magnitude negative spectrum will also be identical. It will be like this, right? So instead of taking this spectrum, what I'm going to do, I'm going to take one tone, an audio tone, some other color, maybe here and here. And I call this, we have been calling it V in. So I'll use a slightly different terminology now. I'll call this FBB. BB stands for baseband frequency. Okay. So I'll define why we are calling it baseband later on, but for now, let's go with the terminology, right? So this is the input frequency, the input tone. Input tone, which we extracted in the last class, which was my audio signal and so on, right? So if we multiply these two in time domain, in frequency domain, what's going to happen? They are going to convolve. So in frequency domain, so I'm going to get tones at, obviously around DC, will I get something? Yes. So because if I convolve, I'm going to essentially, this half term is going to give me two tones, one at specifically the same place where these tones were, but magnitude will be half. Then the next one will come around FC, right? So this will probably be somewhere over here. The next one is going to come around 3FC. So obviously it's not drawn to scale. So I hope that doesn't create any confusion and so on, right? So out of these, right, which one is the desired tone for the frequency of our choice? Pardon? So around FC is our desired tone. So is that evident, or is, or do you want me to explain this in a different way, rest of the class? Okay, fine. So if we agree with the fact that this is the desired tone, so if you cannot have only right-sided frequency desired tone, the negative frequency automatically becomes a desired tone. These are desired. So by definition, everything else is undesired. And now if I have to find out the efficiency of this guy, so I have to basically take the strength of the desired tones and divide it by the strength of all the other tones, right? Because I can do it in frequency domain, I can do it in time domain. Information is the same. All I have to do is extract the power. So whichever is more convenient, I'll use that. Sometimes I'll extract the information in frequency domain. Sometimes I'll extract the information in time domain, whichever is more convenient. Yes.
The highest strength tone undesired one around 0.
Yeah. So around 0, is there a frequency translation? Right. But that's a good question, right? So why isn't that the tones around FBB the desired tones? Because we desired mixing operation. We wanted that FBB tone to go somewhere else. If FBB is, let's say, 10 kilohertz and FC is, let's say, 1 gigahertz, I would like that FBB tone to go to around 1 gigahertz plus 10 kilohertz, 1 gigahertz plus minus 10 kilohertz, right? So that's why that becomes the desired and everything else becomes undesired. Fine. So let's see. I mean, let's now figure out the power. So instead of figuring out the power after the mixing operation, what I'm going to do, I'm going to figure out the power of the desired components in SD of T, because ultimately you are multiplying. All you are doing is multiplying the input with SD of T, right? So that multiplying operation is only scaling. There is two things. One is frequency translation that is happening, and the scaling is happening. So in a calculation of efficiency, that scaling part will get cancelled, right? Something in the numerator, something in the denominator, the scaling part will get cancelled. All of them interested in the frequency translation parts. So that information is only embedded in SD of t, right? The frequency translation in SD of t. So all I will do is find out the corresponding tones, which gives me the frequency translation, desired frequency translation in SD of t. That will correspond to the desired part. Everything else is the undesired part. So I'll divide by the desired by total. That will give me the efficiency, right? So essentially what I'm looking for is the strength of the tones at FC divided by the strength of all the tones, right? So efficiency, so in this case, is strength of tones at FC in SD of t divided by strength of all tones. In SD of t. Fine. Okay. So again, when I say strength, in this case, even though in the previous example, we didn't take any numbers, but in the previous example, we basically were dividing, we are trying to figure out in terms of current ratios. But when we say strength, we essentially mean power, right? So, so when you have to find out power, all you have to do is, in terms of when you are trying to find out power from a frequency spectrum, all you have to do is square the strength of the tones, right? So strength of the desired tones in FC is what? The top one is 1 over pi squared plus 1 over pi squared. So this is 2 over pi squared. Fine. What about the strength of all the tones of SDT? So essentially the question. So bottom one is essentially summation of fine. But this is an infinite series, right? This is an infinite series. There are standard solutions available for infinite series, but there is an easier solution. The easier solution is, this is essentially the power of the waveform. If you have a periodic waveform, it is always easy to find out the power in time domain, because all you have to do is take one cycle, right? So this is equal to power of SD of t. And what is SD of t? Again, so to 1, 50% duty cycle. So what is the power? Total power, half, right? So all I have to do is integrate this divided by TC for over one cycle, correct? So which is equal to half. So essentially the average value of ST is the power, correct? So essentially now, which brings us to an efficiency of 2 by pi square by 1 over 2, which is equal to how much? 4 by pi square, right? Which is 40% approximately, 0.4. Pi square is 10, which is not bad, right? So at least in the previous example that we did, more than 50% of the power was even taken away by probably the bias current, then some part was taken away by the linear term. Here looks like we are getting much better than that, right? But you can do even better. You can do even better, because as you can see, the strongest tone is the DC tone, right? The strongest tone is the DC tone. And if I look at this ST waveform and I want to cancel out DC, what can I do? Okay, mathematically, what you are planning to do to this waveform to cancel out the DC. The DC is how much? Half. So basically subtract half, right? That is fairly simple. You are subtracting a DC, right? That is fairly simple to do in circuits, right? You just put a capacitor, DC gone, right? Alternatively, if you are doing differential signaling, right? If you are doing differential signaling, then you will have one input which is probably going from 0 to 1, the other will be from 0 to -1, or 0 to VDD, or 0 to minus VDD. If you're not comfortable with negative values, then you can say one is around some common mode, goes from 0 to VDD, and another goes from VDD to 0. So differentially, they become VDD to minus VDD. So logically, they become, in terms of 1 and 0, they become 1 to -1. So in that way, the DC also goes off. So you can improve the efficiency even further, right? So you see, this is a much better way of going about designing a mixer. Okay. Any questions? By the way, I hope you are convinced that this is the linear circuit. Why do I say it's a linear circuit? Let me go back to this waveform, this INT and this thing. So when I say it's a linear or not, what test are you going to do? No. What is linear? What are the two properties of linearity? Superposition and homogeneity, right? Homogeneity is not a problem because homogeneity means here, whatever happens here happens in the other part of the material. That's not a problem here. But superposition, does it hold? Does superposition hold good? Superposition means what? You have scaling, right? You input, you scale. If I scale V test by a factor, will INT scale by the same factor? It is going to, right? And if I apply V test 1 and V test 2 and add them up and do that experiment individually, will it lead to the same output, right? So it is linear. But this is not time invariant, right? Because if I shift V test, the output doesn't shift accordingly always, right? An example that I gave at the end of the previous lecture was, let's say you are giving inputs only when the switch is on, and you are going to get some output. Then you shift the input in such a way that they align with when the switch is off. You're not going to get any output. So this clearly they are not a shifted version of each other. So this is time variant. On top of that, this is periodically time variant, right? So the characteristics of the switch is periodic. It is because of that periodicity you are getting the tones, right? So because it is periodically time variant also, this is often referred to as LPTV network, right? So this is often referred to as a linear periodically time variant circuit, right? So these are often referred to as, where should I write somewhere? An example of, I shouldn't say this is. Okay. So till now, I mean, this probably is a term as of now. Later on in the course, we'll spend considerable amount of time on this, right? So till now, it's an overview. Let it remain in the overview stage. But at least you have an idea of why an LPTV network is useful, right? Other than that, you will not be able to use your cell phones. Okay, fine. So now we had a question. Okay. So we had a microphone. Then we had a sensor, which converted signals V in T, or let me now call this VBBT. I'll just change the terminology, which had a frequency component of FBB. Then we used a mixer, right, which was a square wave, which means it had frequency component of FC plus minus I should say basically FC plus minus NFC, or let me simply say DC plus, okay, I'll just say FC plus minus NFC, right? Where N can be an integer. If it's not square, 50% duty cycle, you might get all, right? So let's keep it general. So next what? Next is what? So we have achieved frequency translation. Now I have to transmit it, right? Ultimately, the whole goal is to transmit it over a wireless channel, right? If that was not necessary from the start, we could have as well not do any frequency translation. A simple wire would have been. So we need to send it across free space. So for that, we need an antenna. This is not an antenna design course. We'll assume the antenna exists. Size of the antenna will be of the order of 1 over FC now, right? So because FC is high, size of the antenna will be manageable. Now, as it turns out, an antenna, again, I am not going to prove this, but if you have taken any RF course, you will know that the antenna can be designed to tune it for an impedance of the free space, which again can be designed in, can be modeled in some way. Typically, that impedance is kept at 50 ohms, right? So we can, for the purpose of this course, an antenna corresponds to a 50 ohm impedance, a grounded 50 ohm impedance. One side is ground. You cannot have the other access to the other terminal. Okay. So this is what we will model our antenna as. So I have a 50 ohm impedance. So now we have a frequency translated block. I connect it here. Yes. Oh, that is a part of antenna design. So as it turns out, impedance of free space, you can model it as 50 ohm. And for maximum power transfer, you need to have the antenna impedance to be matched. The intuitive understanding of that is an EM waveform. Whatever waveform in the free space, you do not have voltage and currents, right? You have E and H, right? E and D. Before the antenna, one side of the antenna, you have I and V. On the other side of the antenna, you have E and H. Then how do you go from I and V to E and H? That's where antenna comes in, right? So, but how do you equate the both sides? For any type of sensor or actuator, when the domains differ, the only thing that is common is power. So you do E cross H in the EM domain, pointing vector and so on. Then you get some power. You equate that to I and V, I times V in this domain, and then in current domain, right? And then you equate, and you will get a proportionality constant, which will mimic like something, and that turns out to be some function of permittivity of space and so on. And those you can tune in such a way that they come up to 50 ohms, right? So again, I mean, there are some historical reasons, again, why do you want it to 50 ohm and all, so, but it can be done. So we'll go with that it is 50 ohm. Okay, so now if I connect directly the mixer to 50 ohm, do you see an issue or this is fine? Maximum power transfer is an issue, but even bigger than that, there's a much bigger issue. This can land you in court. Yeah, right. So essentially the problem is when you this part I didn't mention explicitly in the previous lecture, but when you are translating something at a different frequency, and if you find that this frequency suits me, it's very obvious that somebody else will also want to use that frequency because it might suit everybody else. So you cannot arbitrarily choose a frequency of choice. So you have to get special permission. Government auctions the spectrum, and you hear so many things in the news that this spectrum goes to this person, this company, and so on. So as it turns out, you have specific frequencies, carrier frequencies, in which you can transmit your carrier at. Okay, so around the carrier frequency, you probably will have few hundreds of kilohertz of bandwidth that you can use to transmit. If you are transmitting only text or voice, if you want to transmit video, you will probably require the bandwidth required to transmit a video signal, which is of the order of few tens of megahertz, can go up to hundreds of megahertz, depending upon the fidelity of the video. So the moot point is you have specific frequencies in which you can transmit. You cannot transmit it anywhere else. You cannot say that my mixer generates NFC, what can I do? Not possible, right? So you'll get to court. So then what is the solution? Pardon? So you have to basically knock off all the other NFCs, right? So essentially, whatever you found here, so these have to be knocked off. The DC part will get knocked off fairly simply because if you just put a capacitor, right? So essentially what I'm saying, this can get knocked off easily if I put a capacitor. The others are not so simple. So you'll have to knock them off using some sort of filter. So as you pointed out, it is the easiest way to do that is put a bandpass filter around FC. So I'll put a bandpass filter. Again, this is not a pulse in time domain. This is a bandpass filter. An ideal bandpass filter, right? Again, doesn't exist, but the simplest bandpass filter you can think of is an RLC filter, right? So let's go with that. Let's assume you have some attenuation at out of band frequencies for NFCs, and you only FC translates. Fine. So now we have only FC here, right? And the others are negligibly small. And then I connect it here, right? So now the question is, will it work? So to understand will it work or not, let's take some numbers. So let's say this sensor output is an audio sensor. Let's say the IV of the sensor is of the order of maybe some few millivolts, right? So let's say V is equal to, I'm just taking rough numbers. I mean, these are not sacrosanct numbers. Let's say I is equal to 10 milliamps. Okay. 10 milliamps itself is very large. It's probably of the order of 100 microamps or so. So 0.1 milliamps, right? So typical, the power in that you are getting is what, about 1 milliwatt by 2, right? So less than a milliwatt. If there is no loss anywhere in the system, then you can probably transmit at max how much? The question is, let's say you have a system which is lossless. Here you have a 50 ohm load. The input is power in is, let's say, half a milliwatt, right? Which itself is very generous. You will not get, by the way, this is not milliwatt, right? So this is micro. Milli times milli is micro, so half a microwatt. So if the system in which it is going into is lossless, what is the maximum power that you are going to get at the output? 0.5 microwatt, right? The maximum power this is going to radiate out is 0.5 microwatt. With 0.5 microwatt, you cannot even hear from here to the first bench, right? So it's useless. So what can you do? You need to amplify, right? Somewhere in the signal chain, you need to amplify. So you might want to amplify before the mixer, after mixer, before your bandpass filter, after the bandpass filter. Those are system requirements. Okay, I'm not sure how. Does it come back? Generator starts or something? Yeah, I can, but cannot be recorded, right? Okay, so with this, you'll not be able to, I mean, we were saying that we need to put an amplifier somewhere. Now, where you need to put an amplifier is a discussion that we can have later on, because that requires some system level nuances. But let's assume we need an amplifier. Okay. So somewhere we need an amplifier. So I'll just put an amplifier. The amplifier also needs a supply. So now, the question is, what type of amplifier do we need? In this case, what type of amplifier have you learned till now? In other courses that you have done? Anything, right? Common source, common drain, common gate, and so on, and differential amplifier, two-stage, multi-stage, but everything is a common source amplifier only, because that is the only stage that gives you a gain, right? Then you basically mix and match and do all sorts of trickery to fix something else. But at its core, everything is a common source amplifier, right? So let's see if a common source amplifier does this job. So I put a common source amplifier. Some biasing, and this is now at FC, right? So this is frequencies around FC. So FC plus minus FBB, right? But if FC is 1 gig or a couple of gigs and FBB is 10 kilohertz, then for all practical purposes, okay. So in this case, we have good old common source amplifier. You have VDD, and obviously you have to AC couple this, otherwise nothing will get biased. This is 50 ohm. So typically, I'll just throw out some typical numbers. Standard power amplifier of any good probably will have a power requirement of the order of 10 milliwatt or so, right? So a 10 milliwatt translates to what? So this is antenna, you have to transmit 10 milliwatt, right? So 10 milliwatt corresponds to, and if this is supposed to be a sinusoidal signal, so this is, let's say, Vp cosine omega 2 pi fct. So they should correspond to Vp squared by 2 times 50. In other words, your Vp squared is 10 times 100 milliwatt is 1 watt, or Vp is 1 volt, right? So essentially, you would want a sinusoid here, which goes from mean is 0, obviously, because on the right-hand side of the capacitor, no DC can flow. So this is 1 volt, this is minus 1 volt, right? Okay, which means you want a current through the 50 ohm resistor, which has an amplitude of how much? One volt by 50 ohm is 20 milliamps, right? So you want a current pulse, you want to, or rather not a pulse, you want a current sinusoid, which is also, this is 20 milliamps minus 20 milliamps. Fine. So this 20 milliamps, so when will it get to plus 20 milliamps? So let me rephrase the question. So under what condition of M1 will you get plus 20 milliamps flowing into the 50 ohm resistor? And you can assume this capacitance to be infinitely large. So is M1 fully on or almost close to off? Yeah, right. So when plus 20 milliamp means the direction of the current is this side. So which means it can only come from the supply, right? So this is plus 20 milliamps. And naturally, when we have the negative 20, which means it has to come from here. Since I'm putting the direction, I'll have to keep. Pardon? Okay, so the question is, how did you figure out the transistor needs to be off? So, maybe the better way to approach this statement, the question the group raised is, how do you figure out for the output to go to plus 1 volt or the current, most of the current to flow into 50 ohm? Why should the transistor be off? That's not a generic statement. Transistor can still be on, but between the case, let's say the transistor is right now biased only, no input is connected, right? That is it's only DC biased, right? So under this condition, what is the minimum amount of current that you would want the transistor to have so that both these conditions, that is plus 20 milliamp and minus 20 milliamp at the load, is met? Let me rephrase the question, right? So maybe the question is not very clear. The condition is given, right? I want 20 milliamp plus minus flowing into the load. Okay. For this to happen, under bias condition, right? When there is no input connected to the transistor, what is the minimum current requirement in the transistor? Is it 0? Is it some non-zero value? Is it infinitely large? What? Some ID is required. Okay, let's start from there. Why is some ID required?
So we have applied the bias one.
Right.
So it's a no signal condition.
Right.
So there is no input signal is coming.
Sure.
So for the bias applied, so there will be some current.
Sure.
Maybe a bias at saturation. So the idea is to do saturation current.
Saturation current is required. Okay, let me then even ask a simpler question. Why is saturation current required? So why do you want to bias? Okay. Come again? To get high GM value, yes, true. We get to get higher GM value, but I mean, if the only constant that I give you is this plus 20 amp minus 20 milliamp, will simply biasing at saturation be sufficient, or there is any other constraint? It has to be on with what value of current?
20 milliamps to flow inwards.
Pardon?
20 milliamps to flow inwards.
24 milliamp to flow inwards. If it didn't have 20 milliamps to flow, what would have happened? Right. So essentially the problem is, so let's say I have IDS, right? Let's say I biased it with 10 milliamps, right? Hypothetical scenario, I biased it with 10 milliamps, and I apply an input. Now I apply an input and applied an input such that so if 10 milliamp flows through this, the 10 milliamp is also flowing through the resistor under bias condition, and apply an input is such that the transistor is maximally on, right? So in that case, what will be the current through the 50 ohm load? Assume the capacitor to be shorted and all at signal frequencies. When the signal was not applied, no current was flowing through 50 ohm load. Now the signal is applied. How will you get 20 milliamps out of it? So will the KCL at that node get satisfied at this node? Okay, we're way out of time. Okay, so maybe I'll take one more minute. True. Agreed.
So to keep the KCL, whatever comes,
Okay, so let me go the other way around, right? So let me go the other way around. Probably that will be a more intuitive way of understanding. So let's say I am looking for the case where the 20 milliamp has to flow into the 50 ohm resistor, right? So I have biased it with 10 milliamps right now. So 10 milliamps flows through the bottom and 10 milliamp is coming from the top. And I want 20 milliamp to flow into 50 ohm. So for 20 milliamp to flow into 50 ohm, what should transistor do? It should pump current upwards, not incremental current, absolute 10 milliamp current pumping upwards. Is that possible? No, right? So what is the minimum current that is required for the transistor so that 20 milliamp flows into 50 ohm? Has to be 20 milliamp because transistor can at max go to 0. It can at max go to cutoff, right? So you need at least 20 milliamps always flowing into the transistor, at least in this configuration of common source amplifier, right? Right. So we'll stop here. What I would like you to do is do this analysis, very simple analysis of if this is the condition where I have 20 milliamp current flowing at the DC bias, what is the efficiency of this configuration? Right. Again, efficiency means power delivered at the output divided by the total power in the total power consumed. Right. We'll meet on Saturday, 11:15, DA 2 to 9. Thank you.